Okay, so now we're going to talk about something called eigenvalues and eigenvectors, which are enormously important in mathematics, not just in linear algebra, but also in differential equations, in real analysis, operator theory, engineering, physics. Extremely, extremely important. You could say that quantum physics is based on eigenvalues, eigenvectors. So I'll leave you with that. So what's the motivation behind this concept? Well, we've been talking about matrix equations that have the form AX equal B. Okay? In this sort of equation, A is a matrix, X is a vector, and B is another vector. Now, this matrix multiplication is quite a bit more complicated than ordinary multiplication. If you have a n by n matrix, you're going to have n squared operations in order to compute this vector B. But in some cases, the action of the matrix A may be much simpler. For instance, if I take some equation like this, lambda, that's a commonly used letter for a scalar, that's a Greek lambda, times x equals b. Okay, that's much easier to compute, and there's a much simpler relationship between x and b if this is just a number. Now, in some cases, when you multiply a vector by a matrix, you end up with some constant times that same vector. Okay, and when that happens, we say that the vector is an eigenvector. So that takes us to this definition right here. If we have a square matrix of size n, and a non-zero vector, non-zero column vector of dimension n, then lambda is a eigenvector, then x is an eigenvector of the matrix A with eigenvalue lambda if AX equals lambda x. In other words, for this particular x, for this particular matrix, the multiplication of the matrix A with the vector x has this particularly simple form as just a constant times the original vector x. Now, you might think that that means that A has to be a very simple matrix, but it's not true. Let's look at some examples. If you actually do these multiplications using SAGE, you'll find that this matrix A times x gives you a vector that's actually equal to 4x. That's certainly not obvious looking at A and x, but it turns out to be true. On the other hand, if you multiply A by y, it turns out that you get 0y. It turns out that y is in the null space of A. But in that case, y is still an eigenvector of A because it's a scalar times y. So any vector in the null space of a matrix is an eigenvector. Here's another case of an eigenvector. So you see this one matrix A has two eigenvectors with two different eigenvalues. Actually, three eigenvectors with three different eigenvalues, and there's more coming. It actually has four eigenvalues. Well, this eigenvalue is the same as that one, but it has four different eigenvectors with some of them have different eigenvalues. Okay. Now, so we've shown four. Are there more? Yes, there are. If you multiply any eigenvector by a constant, it's still an eigenvector. And you can see why that's true. If I take 30 times an eigenvector, then when I multiply that, I'm going to get 30 times the result. 30 is still a constant, so I'm still going to get 4 times, in this case, 4 times the original vector. On the other hand, if I have two different eigenvectors with the same eigenvalue, you can work this through. Take the sum of those two different eigenvectors. You take AV, V is the sum, I can write V as Z plus W. I can break apart the sum, I distribute in the matrix. Since Z and W are both eigenvectors, I can rewrite as 2Z plus 2W. I can use distributive law to remove the constant, but Z plus W is V. So in fact, if I add two eigenvectors with the same eigenvalue, they have to have the same eigenvalue, I'm going to get another eigenvector. Okay. All right, so look, the set of eigenvectors for a particular eigenvalue is closed under scalar multiplication, and it's closed under vector addition. So what does that mean about the set of eigenvectors associated with a fixed eigenvalue? You guessed it, that means that the set of eigenvectors that are associated with a fixed eigenvalue, form a subspace. Okay, so here's where notion of subspace becomes in a very powerful way. Okay. Right now, here we also have the null space. As we said, the null space is a special case of the set of eigenvectors associated with a fixed eigenvalue. The null space is the set of eigenvectors associated with the eigenvalue 0. Okay, so that's one special. Null space is a special case of such kind of subspace. These subspaces are actually called eigenspaces. Okay, so I could say the null space is the eigenspace for eigenvalue 0. Okay, so that's our little introduction. We'll stop there.